as we've mentioned previously, when a ketone has alpha CH protons, alpha CH bonds, when it's treated with a base, deprotonation gives you an enolate. So if we have a base, we do a deprotonation here to give us an enolate. We get a resonance form in which the carbon-based enolate becomes a oxygen-based enolate. And the proton is rather acidic here, right, because of this resulting resonance form, resonance delocalization. And this resonance delocalization comes from the fact that you have an owl-like resonance form, series of resonance forms. Right, so it's a 4-electron, 3-atom system. And you might recall that these 4-electron, 3-atom systems are very similar to the regular allyl system. So if we were to talk about the allyl anion, for example, and we were to draw the molecular orbitals for the allyl anion, we would have 3 molecular orbitals, which derive from the 3 atomic orbitals. These would be the psi1, the psi2, and the psi3 star. In the lowest molecular orbital, we would have 0 nodes, then 1 node, and then 2 nodes, respectively. In the lowest energy molecular orbital, we're going to have a series of orbitals which are all in phase. In psi2, this switches, so we have 1 node directly in the center. And in the case of psi3, it resembles the shape of psi1, but it changes each time. If we were to talk about the number of electrons that are in these orbitals, we have 2 electrons in the psi1, 2 electrons in the psi2, no electrons in the psi3 star. And we say that these orbitals are the pi, the non-bonding pair of electrons on carbon, and the pi star. And by analogy, this is the HOMO because it's the highest occupied molecular orbital, and the pi star is the LUMO because it's the lowest unoccupied molecular orbital. And so this is the molecular orbital description for the allyl system. Well, what would happen if we were to take a look at the molecular orbital description for the 4-pi-electron, 3-atom system of the enolate? In the enolate, the molecular orbital description is, but it only changes slightly, and that's due to the presence of that electronegative oxygen atom. All right, so if we have the enolate, let's just say we've got an oxygen with a negative charge. Okay, 3-atom, 4-pi-electron system. We're still going to have 3 molecular orbitals, so those are the psi1, the psi2, and the psi3 star. Okay, we still have the same types of lobes. All right, but this time, the sizes of these orbitals change. So I'm going to put the oxygen atom right here. Okay. All right, so again, I've got 0 nodes in that lowest molecular orbital, 1 node in the psi2, and 2 nodes in psi3 star. But notice that in the psi1, the wave kind of looks like this, in which the oxygen bears the greatest lobe. If we go to psi2, psi2 looks like this, where we've got 1 node in between, directly at that carbon atom. And this time, the greater lobe is on the carbon atom. And in psi3 star, it looks like this, where we're changing the phase each time. Okay, so if we were to draw electrons in these orbitals, again, we would have 4 electrons total. And so that would be pi, non-bonding level, and then the pi star. And again, we've got the HOMO here and the LUMO. Okay, so let's talk a little bit about the differences and similarities between this system and the allyl-anion system. In the enolate, the molecular orbital description tells you a few things. The first thing it tells you is that the total charge, and so this would be psi 1 plus psi 2, the total charge is greater on oxygen. Okay, so how do we know that from this molecular orbital description? What we need to look at is the size of the lobe on oxygen. If we were to add up the sizes of those two lobes on oxygen and compare those to the size of the lobes on carbon, we would see that the sum of the lobes is greater for oxygen than it is for carbon. Why don't we care about psi 3? Well, psi 3 doesn't have any electrons in it, so it can't have a negative charge. The other thing that's important, though, is that in the HOMO, the charge is greater on carbon. And so this is going to have an impact on reactivity. Often, when you're reacting an enolate as a nucleophile, you have two choices for it to react in the HOMO. You can either react at carbon or on oxygen. And so in this particular instance, what we're saying is that the greater charge is on carbon. All right, so how do we decide which one is going to react? Well, actually, that is determined by the experimental reaction conditions. Okay, so under dynamic control, so these are high temperatures, longer reaction times. Under thermodynamic control, the reaction normally occurs at carbon. And the reason it occurs on carbon is it's to maintain the greater bond strength of the carbon-oxygen bond. Remember, we said that the carbon-oxygen bond was really strong. And so we can take this enolate here, and if we were to take this enolate and react it with, let's say, methyl iodide, the way we would react this is by reacting the carbon atom, not the oxygen atom. And so we get this really stable carbon-oxygen bond, and now we have a new bond to the carbon atom to the methyl group. This changes under under kinetic control. So under kinetic control, so these are low temperatures, shorter reaction times, right? The big lobes of electron density, right, on either carbon or oxygen, right, means either can react and this is driven by electrostatics. what I will say is that normally what happens is that oxygen is going to react. Okay, oxygen is going to react when you have electrophiles like H plus or silicon-based electrophiles. Okay, so the answer here, an example here, is to take this enolate and either react it with H plus, right, and that's going to give us a nucleophilic attack, right, driven by the charge attraction between the point charge H plus and the big lobe on O minus, and that's going to give us the enol. And then, of course, that tautomerizes into the ketone. What may be more sort of interesting is taking this molecule, this enolate, and reacting it with trimethylsilyl-chloride. Right, so TMS stands for trimethylsilyl-chloride. And you can draw arrows in this way, kind of a SN2-like reaction, to give you this species. OTMS, or if we wanted to draw it out, we could say O silicon with 3 methyl groups hanging off. Okay, so this is a trimethyl silyl group. And this product that we have here is known as the silyl enol ether. And this particular functional group is going to be important as we go throughout this chapter. All right, so now that we know a little bit more about how these enolates react, let's take a step back and take a closer look at how enolates are formed. Say we have a molecule that bears more than one type of alpha CH bond. How do we control which one is deprotonated? All right, so let's consider the following molecule. We have this alpha methyl ketone, and we could potentially deprotonate with a base to give us an enolate on, let's say, the right-hand side. And so we're going to be deprotonating this one, and I'll just draw that in with a color. All right, so we're going to deprotonate this this one here, and that's going to give us the enolate like this, which can undergo resonance delocalization to give you the enolate that looks like that. Okay. All right, so we call this the Thermodynamic Enolate. But we could also take a base and deprotonate in the opposite direction. We could deprotonate, for example, let me use green, this one. And that would give us the Kinetic Enolate. So the Kinetic Enolate would look like this. You could draw a resonance form for that. All right, so how do we control which of those two protons is being deprotonated? Let's start with the kinetic enolate. Right, so deprotonation of the kinetic enolate, or deprotonation of one of those two green hydrogens, I'm not drawing in the second one, deprotonation is less hindered. It's not only less hindered, there are statistically more protons. Right, so statistically more protons available for deprotonation. And so what we say is that the delta G double dagger, the transition state for deprotonation, is lower. The activation energy is lower. The transition state is more pre-organized. It's more pre-organized for deprotonation. So how might you favor the kinetic enolate? So you favor the kinetic enolate by, one, using lower temperatures. So things like 0 degrees or minus 78 degrees Celsius. Using a bulky base, right, to disfavor deprotonation of the more hindered site. Okay, and some examples of these types of bases are things like LDA, which has the structure here, lithium diisopropyl amide. There's also KHMDS, right, and which is kind of the potassium version of LDA, but it has a couple of new features. It's got a TMS group off of the nitrogen instead. And so this is potassium hexamethyl disilazane, but you don't need to know that. And then LTMP, which has the following structure. So it's lithium tetramethyl piperidine. And these are all bulky bases that can be used to favor the kinetic enolate. Now, why might we favor the thermodynamic enolate? Deprotonation here is sterically more congested, but it gives a more highly substituted enolate. And we know that enolates are kind of similar to alkenes in terms of stability. When they have higher substitution, they are, of course, more stable. And that's because of things like sigma donation and resonance. Right, so it is true that deprotonation is more sterically congested, but if you could do it, it gives a more highly substituted enolate, which is more stable. Right, so how can you favor the thermodynamic enolate? Well, what you can do is after adding a base at low temperature, right, allow the temperature to warm to, if you started at minus 78, 0 degrees, or if you started at 0 degrees, room temperature, in order to equilibrate. And so what's happening here is when you add it at low temperature, you're probably going to form the kinetic enolate first, but as you warm it up, there is an equilibrium between deprotonation to form the kinetic enolate and deprotonation to form the thermodynamic enolate. And now you have enough energy to make that deprotonation at the more sterically hindered site, and so it will equilibrate into the thermodynamic enolate. The second thing that you can do is use a less bulky base. All right, so things like sodium hydroxide, sodium ethoxide, sodium methoxide, triethylamine works, diisopropyl ethylamine also works, and these types of bases are really good. And the third thing you can do is a little bit different, but it's actually similar to what we just had on the previous slide, is to use TMS chloride as a Lewis acid, then add triethylamine as base, and what this does is the TMS group, you can think of it as just like a bulky proton, right? So it will make the sigma CH more acidic, right, due to more sigma donation. And so the way you do this is by taking, let's say, TMS chloride. The TMS group you can think of as just a bulky proton, so it attacks the silicon, makes a positive charge there, and now this proton is a lot more acidic, and so you can undergo deprotonation with triethylamine, and what you'll get is the silyl enol ether. So those are ways of making the kinetic and the thermodynamic enolates. And so we can control which enolate we form by altering the reaction conditions. But enolate formation is not just an intermediate bond treatment with a ketone. Treat a ketone with a base forms an enolate. But you can have other functional groups that can also become deprotonated at the alpha position, and they have a similar reactivity. And so let's see how a couple of these functional groups are similar. So let's take a nitrile. How might a nitrile be similar to an enolate from a ketone? All right, so if we have acetonitrile, and we treat acetonitrile with LDA and THF at minus 78 degrees, we're going to generate an enolate-like reactivity. Now, where does this come from? This comes from the fact that you've got alpha CHs to a pi system. And so you can take LDA and do a deprotonation. And so we can get this species here, which can resonance delocalize up into the nitrogen atom. Just like we would for an enolate on carbon delocalizing into the allo-like system to give you a negative charge on oxygen for a ketone. And so this has got enolate-like reactivity. So you can take nitriles and deprotonate alpha to the CN bond to give you enolate-like reactivity. And then that can go on and do a reaction with an electrophile. Esters also do the same thing. And so let's say we have this system. We take LDA here. Again, THF minus 78 degrees. I won't draw it in. But we can do a deprotonation. That gives us a carbon-based enolate. And that can delocalize to give you the oxygen-based enolate. And we normally draw enolates with the negative charge on oxygen because oxygen, of course, is more electronegative, and so it's more stable that way. Aromatic compounds can also deprotonate, especially heteroaromatic compounds. Right? So let's say we have this heteroaromatic, and we were to treat this heteroaromatic again with LDA, and so here we go. We've got alpha CHs right here, and you can kind of think of this motif as being enolate-like. And so we can get a deprotonation to happen. To give us this. And then that can, of course, delocalize. To give us that nitrogen-based enolate. Now, we might not think that this is very favorable to have the nitrogen-based enolate, so maybe the true Lewis structure lies more towards the carbon-based enolate, because in order to form the nitrogen-based enolate, we would destroy aromaticity. And nevertheless, it has nucleophilicity at the carbon atom. And the final one are the nitro compounds. And so let's say we have this nitro compound, and don't forget the Lewis structure of a nitro group. Okay, we got an alpha CH right there, so if we were to treat with LDA, again, we've got kind of ketone or enolate-like reactivity here. We could do a deprotonation with LDA. And so we get deprotonation and we get carbon-based enolate. Which can undergo resonance delocalization to give us the oxygen-based enolate. Okay, so we know how to now to make these enolates. Once formed, these enolates can react with a broad range of electrophiles. And so really the rest of the section of this course deals with the reactions of these enolates with various functional groups. Right, so we're just going to have an overview slide here. So the reactions of enolates that we're going to be discussing really fall into four categories. The first category is the reaction of an enolate, and I'll just label this X. Reaction of an enolate with aldehydes and ketones. Okay. Second thing that enolates could react with are esters. Okay, the third thing that we're going to talk about enolates reacting with are alkyl halides. And finally, the fourth thing that we're going to have these enolates react with are what are known as alpha-beta unsaturated systems. Alpha-beta unsaturated ketones, esters, aldehydes, etc. So alpha-beta unsaturated carbonyls. If we're thinking about where that alpha-beta term comes from. It comes from the fact that you've got a double bond, an unsaturation unit in between the alpha and beta carbons. And so the rest of the course is really going to focus on what is the product for each of these reactions of enolates with various electrophiles.